So hi, everybody. Welcome to Cassandra and Spark SQL. You don't need functional programming for fun. This is going to be a talk all about how you can do all the great things that you want to do in Spark without ever writing a line of Scala. And to quickly kick things off, that's me. I'm Russell Spitzer. I'm a data stacks engineer. I've been working with Spark and Cassandra since Spark 0.9, if you remember those good old days. And I've been working with Cassandra since about Cassandra 1.2. And I am a recent Scala convert. I think functional programming is awesome, and I think everyone should check it out and take an interest in it. But I know that not everybody is really into functional programming. And because of that, I'm going to tell a little story here. And it's about why you can do all of those great things in Spark that you want to do using just SQL. So first, I'm going to go into a little bit about why this is an attractive proposition. Next, I'm going to talk a little bit about the Spark Thrift Server, which is a basic vehicle you can use to start running your SQL from multiple clients against the Spark cluster. And finally, just a few details on how you actually write SQL for Spark to interact with other systems, including Cassandra. So to begin with, you have a lot of options when you're about to get started on a Spark project. Obviously, there's Scala, Java, Python. There's all of these language options. And it can be a little overwhelming, especially when at the same time you're being given this entire brave new world of functions and concepts that you really need to internalize to be effective. But and while this whole system, Spark, is built on Scala, and I think Scala is really awesome, I know that to a lot of people, when you start seeing lambdas and monads and all this kind of stuff, it really looks a little bit more just like a bunch of gibberish. And that can be a real turnoff to a lot of people who were really excited to get into the big data world and all of a sudden run into this big block of how are they going to manage their jobs and how are they going to build files and things like that. And realistically, there are time constraints about all of this, right? If you're just about to enter into a new project and you've decided Spark is going to be part of your tool chain, it often doesn't make sense to also learn a new language at the exact same time. So let's talk about how we can use Spark SQL to use something we already know and understand how to use and use it with the power of Spark. Now, this has been gone over a bunch of times at this conference already, but basically what's happening is you can write in SQL, and through the magic of Catalyst, all of these great kind of things happen, and basically, the end of the day, work is going to happen distributedly on your data set. Now, what I really like about the Spark SQL approach is you really don't have to know about the second half of this. All you really need to know is how to write the SQL to get the work you want done, and then you send it. So the easiest way to access this directly is using this kind of API within Scala. And you might say, Russell, you just told me this whole bunch about how we don't need to know any Scala. I don't have to learn SBT. I don't have to do any of this. Because inside of that, all you really want to have to do is that little bit right there. And the answer to this is there actually is a built-in client for Spark called the Spark shell, the Spark SQL shell, that you can run and comes packaged with Spark. And all it is a REPL where you can type in an SQL expression and get out a result set. Now, this is really great for playing around all by yourself because you write in your expression, it goes into a Spark session in a Spark context. That Spark context spins up all of these distributed resources that are locked exclusively to this context, and you start getting work done. Unfortunately, this is not a great situation when you have other users on site, because those other users want to get in on your Spark session, but they can't because you have an exclusive lock on it and all of the resources that it has. So how can we go from a situation where only one person is able to run SQL to a situation where we can have many people running SQL? And there's actually something already built into Spark that you can use to do that, and that's the Spark SQL Thrift Server. And it works by having multiple users, each using their own JDBC client to connect to the same Spark context. So there's still just an exclusive lock between that Spark context and all the resources, but this time, the actual application itself is receiving input from multiple different users. So here's just a quick overview of some of the things that are important about the Spark SQL Thrift Server. It's got a single Spark context you communicate with via JDBC. It supports all of Spark SQL. But there's two things that I wanted to point out especially which might prove to be really attractive if you're about to start a project in Spark. and that's fair scheduling and the fact that clients can share cached resources. So to quickly talk about fair scheduling, a little of my thunder was stolen this morning when they showed the whole serverless approach inside of Databricks' unified analytics platform. But there's actually a similar thing that you can do inside of the Thrift Server called fair scheduling. Because usually when you have multiple users in the same application that run their own Spark jobs, it's a first in, first out queue. And that means that if user number 1 sends their request and their request takes 20 hours, then it starts queuing up tasks. And if then user 2 comes along and she sends out a really fast request, her request only takes about 5 minutes. She actually has to wait until every single piece of work from user 1 is done before any of her work gets done. So this is not fair, and what we want is something that is fair, and that's the fair scheduler, which will instead behave like this. After user 2 has now submitted their request, and this is done on a task level granularity, they get to start alternating. And with the alternation, that means that their average time to finishing their query is going to be much, much lower. So you get this better way of actually sharing the resources that is existing in the entire cluster. And again, this is something that you can only do when you have a single Spark context. The other cool thing about having a single Spark context that multiple clients are connecting to is the ability to share cached data. So you can basically do this little magical spell up here. And when you do this, it sends a command into your application, the Spark Thrift Server, and tells it that there's data that needs to go into RAM on all of these executors. So it basically loads up cached data onto each of these executors. And the thing to remember is, since all of our clients are communicating with this same Spark context and these same executors, they can have access to that exact same data. So user 2 can come along and do requests on this. So in this particular example, you might say, at the beginning of the day, user A, does a cache on this table and says, I'm going to just cache all the data we computed today, get that set of data into RAM, and then all of the other users, when doing analytics for the rest of the day, can use that same cache without actually having to know about how it was cached. So this is really fun and useful stuff. How do we actually start up the Spark SQL Thrift Server? So in the built-in Spark distribution, you run the sbin start thrift server. And if you're using DataStax Enterprise, which is what we sell at DataStax, it's a DSC Spark SQL Thrift Server start. And the cool thing about these commands is they're actually just like a Spark submit command. So if you're familiar with that or you've seen that in examples, any of the options that you could pass to Spark submit, you can pass through to your thrift server starting. So for example, if I want to include the Spark Cassandra Connector and I'm using the open source Spark distribution, I just have to add the packages option for the Spark Cassandra Connector and point it towards wherever my Cassandra cluster is. If you're using DSC, this is all automatically set up for you, but that's just how you do it if you're using open source. And you'll see this little message which talks about starting up SQL Hive Thrift Server 2. And at this point you might pause and you say, Thrift Server, Hive, I didn't think we were doing anything with Thrift, and I definitely didn't think I was using Hive. I'm pretty sure I'm using Spark right now. So why is all this stuff coming together? To explain why this is the way it is, we're going to have to do a quick little history lesson. For those of you who are Cassandra users from way back in the day, you might say, I remember Thrift. Thrift was a Cassandra protocol that we don't use anymore. Why is it in this application? And the fact is that Apache Thrift is actually a framework which protocols can be built upon and different communication can be built upon. So while Cassandra Thrift and Hive Thrift kind of sound like they are the same thing, they're just two different implementations on the same framework. They don't actually interact. Now, for those of you who are thinking about Hive and wondering, where does Hive come into play here? Well, this is really a slightly longer story, and I kind of say it's akin to the ship of Theseus. And if you haven't heard of this story, it's basically about a boat, and the boat goes sailing around the world. And as the boat goes sailing around the world, parts of the boat break, and they have to get repaired. And they start replacing pieces and pieces of the boat until you've basically replaced every part of the boat. And at that question is it even the same boat anymore? And that's kind of the same thing that happened with the Spark's Thrift Server. So way back in the day, we had something called the Shark server, and this is my boat representation of it. And the Shark server started out with a Hive parser, and it would use a Hive optimizer, and it would basically make a map reduce, and then all of that would just get run on Spark. It would be run on executors and things like that. And then JDBC within the Hive code would be used to return the results. So you can see there's not a lot of Spark in this whole picture. Then this project was stopped, and we moved to the Thrift server. And with that, we also got a bunch of really cool things that you probably have heard of. Catalyst as our optimizer in place of the Hive optimizer, and something called schema RDDs. So everyone here remembers schema RDDs, right? Well, maybe you remember data frames or data sets now. Data sets is what it is. But basically, we've gone through a bunch of name changes, but the component here has basically been the same the whole time. So we go through Hive now, go into Catalyst to do our optimization, end up with data set representation, do all of that cool code gen, and end up with Spark execution and still have JDBC results. But even more recently, the parser itself has actually been pulled from this and is a Spark native processor. So we're actually going completely Spark now through this entire chain of events, except for actually accepting our incoming connections and sending our results back out. So the parts of the Hive server that are actually still part of the Spark Thrift server are really the shell around it. All of the actual parsing, computation, and work is still a native Spark project, or still native Spark code. Almost all Spark. OK. Because it has all of these Hive ancestors and all of this lineage, it actually can use a lot of Hive-based tools. So for example, Spark is packaged with the Beeline tool, which is a JDBC client that's just built in if you want to start testing this out without actually writing your own JDBC application or something like that. You can just run Beeline, and you'll get a little command prompt in which you write a connect statement, which will connect you up to the Spark Thrift server, and you'll get another little REPL where you can type in SQL and get out results. The cool thing about being tapped into this JDBC architecture is now all of those BI tools you like Tableau, you can now connect directly through to any Spark available data source. So for here is an example where I have a table in Cassandra that I'm going to register in the Spark SQL Thrift server, and then I can communicate with it through Tableau. So I'm using Spark Thrift server as an intermediary to connect my JDBC BI tool to my Cassandra data. So you can do kind of cool things like this. And of course, that opens you up to a whole world of possibilities where you can connect all sorts of different BI tools to Cassandra, to Spark, to relational data, and you can join them all together through this intermediary point. So super cool stuff that you can do. But one thing that I want to warn you about is that when you're using the Spark SQL Thrift server, one thing that it does is that sometimes BI tools are a little cruel, and they'll ask for certain SQL, they'll run certain SQL that's a little dangerous. Like, for example, they might request a gigantic result set because maybe they want to do a visualization, or some BI tools like to do a little local caching. And unfortunately, the default for the Spark SQL Thrift server is that when you do a large request like this, it's going to pull all of the data after it's been computed into the Thrift server, and that just blows it up. So that's not great. But there is a workaround, and the workaround is a very not documented feature called the incremental collect, which is going to switch the operation from, instead of pulling the entire result set back at once, to pulling back single Spark partitions at a time. So feeding it through that way, you have a much greater degree of control over how much memory is actually going into the Thrift server before the results are fed back. So this is something I recommend if you start running into OOM issues with a BI tool. Usually when you're controlling the JDBC requests, you know whether or not you're about to get a huge result set, and you can tune that. But with BI tools, we all know it's a little harder to actually know what requests it's going to be issuing. So now that we've done all of this hopeful motivation that has gotten you really excited about writing Spark SQL and working with the Thrift server, let's go over some of the basics on how you actually write this stuff. So we'll start out with registering sources. So you probably saw originally, and you've probably seen a bunch of examples of this so far, where people load up a data frame by doing something like spark.read.format, and you see a whole bunch of code like that. In Spark SQL, you write a very similar sort of thing, but we write it like this. We write create temporary view, and then we name our view. This is the thing we're registering in the catalog. And then we say using, and then we put a format there. Now this is where you would write parquet, or org.apache.spark.sql Cassandra. Don't worry, I'll have that written on the next slide if you're confused. And whatever source you want. And then underneath that are the options for that particular source. So for example, when I'm reading from Cassandra, I need to specify a key space and a table name. And there's, of course, a lot of other parameters that I could specify that would change the behavior of the data source. So for example, this is how I would read the table tab in the key space KS from Spark SQL. Basically, this is going to register a temporary entry in my catalog that is going to map directly to a Cassandra cluster and read the data from it whenever I do an operation on it. So this is really cool. We have no functional programming required to do this. It's all very standard-looking kind of SQL. And what's cool is that under the hood, this is going to actually invoke the exact same code that would have been invoked had you written that Scala or that Python or that R or whatever it was that would have done it. It all goes into the exact same execution pipeline. So you get the same power even though you've done it through a different API. One of the cool things to note about this is in the options for the Spark Cassandra connector, you can actually pass through any of the other options that are available to the Spark Cassandra connector. And if you look on our GitHub, you'll see a whole list of different parameters you can set there. But basically, you can set them all within Spark SQL without actually having to modify your Spark configuration or programmatically set anything up. Another thing to note is that the Thrift Server can connect to an external Metastore. So that means if you have a Hive Metastore running, you can actually make permanent catalog entries that multiple users can all access and use to communicate. A note about DataStax Enterprise is one of the things that DataStax Enterprise will do is it will actually automatically register every Cassandra table as an entry in its own Metastore. So when you're using DataStax Enterprise, you actually don't even have to register Cassandra sources. You'll just have to register the ones for other things that you want to move data into or read from. So we've read our data frame. We've got a table made, some temporary view made. How do we actually write it to something else? So we do that with an insert into statement. And basically, it's got two parts. The first part is going to be where are we sending the data to? And then the second part is where are we getting the data from, or what data are we getting? So this is probably familiar to those of you who have written a little bit of Hive before and some dialects of SQL. And basically, under the hood, it's going to do the same thing as if we had done all of that functional programming to do the data frame read and the data frame write. And what's really great about this is that in this SQL, we don't actually have to know what the underlying implementation of either of these tables is. So arrow could be a Cassandra table, and words could be a JDBC source like an Oracle database. So with just one line of SQL, I can actually move between a NoSQL and a relational database. I can take data from Parquet and insert it into Cassandra. I can take data from one Cassandra cluster and insert it into another Cassandra cluster. I can do all of this without actually having to write a line of code or compile a single file. So this is all extremely powerful and super cool. But one of the things that you might want to do once you start getting into this is start actually analyzing the query plan. And you might see that this code I'm showing up here, which comes from an SQL explain statement, looks a lot like some of the diagrams we've seen at a lot of other talks at Spark Summit so far. Because what you get actually out of this is the same catalyst optimization tree that we've been showing in a lot of other talks. And you'll get to see that, oh, when I do this particular request, it's actually going to pull data out of Cassandra. And more importantly, it's showing us this pushed filters option, which is showing us what filters were made available to the data source itself. So this is where we get into some really cool features of the Spark Cassandra connector, which is that it's automatically able to recognize certain predicates and determine whether or not they can be optimized and pushed down to Cassandra and basically be done at the source. So for example, when Catalyst was looking at this particular request, it noticed that it had to do a filter, and the filter was a greater than on the column C versus the literal 2. So it looked at that and it presented that under the hood, completely invisible to you, the end user, to the Cassandra source relation. And the Cassandra source relation said, C is a clustering column in Cassandra. And for those of you who know a lot about Cassandra, you'll know that that means that that's a query that can be actually run directly on Cassandra itself. So the Cassandra source relation will basically absorb that filter into itself and becomes one of these pushed filters. So internally, it's going to be running SQL where it has this predicate already there. So this minimizes the amount of data that actually has to get pulled out of Cassandra and put into Spark. So this is an automatic pushdown, happens completely without you having to worry about it. There are a few cases, though, where this might be a little tricky, and this is why I'm kind of showing how you do this explain statement, because every once in a while, you might not get the automatic pushdowns you think you should be getting. So for example, here, you can see up at the top, we have a tree here that has a filter statement all by itself. It says filter cast C76 as string, and you're upset here. Why isn't this getting pushed down? It's not in my pushed filters category. And the reason for this is that when Catalyst makes this little tree, it says, C is less than 2017-05-27. And quite reasonably, it says, well, C is a date. If you look in the read schema, you can see C is a date column. And a date is not a string. If a date isn't a string, how do I compare them? I'm going to obviously have to cast one side. So Catalyst decides, well, I'm going to cast the C part. And that's why you see there's a cast C76 as string before it does the comparison, because what it's doing is a string-to-string comparison instead of a date-to-date comparison. And since it needs to become a string before Spark thinks it can do the comparison, it can't be pushed down, because it doesn't trust data sources to apply functions. Long story short, the way we fix this is we give it a little bit of a hint on what we actually mean, which is we cast our literal as a date. So if we do that, it says, I want to compare the column C with the date 2017-05-27, not the string. And since they're both the same type, it can push that filter down to Cassandra. And you'll see in the pushed filters, suddenly our less than is going to appear there as one of our available push-down filters. So once again, we get our automatic pushdowns back. All we had to do is make sure that we were expressing clearly what we actually wanted in our SQL. Oh, sorry about that. So one thing I want to talk about with DataStax Enterprise, in case you were wondering, and I'm sure you were, is that DataStax Enterprise actually has automatic integration for pushdowns against Solr indices, because one of the things that DSE also supports is indexing through search. And we basically provide an automatic optimization of those predicates that if you're running on a DSE cluster with search enabled, it will also automatically convert predicates into a searchable format and run against the Solr indices. So that's a cool little feature. It's really great if you're doing counts, because if you're doing counts against Solr indices, you can get pretty amazing performance because you don't actually have to read any data. You basically just look through the indices and get back your result counts. And the other little thing I'm teasing in here is this difference between this red and this orange bar. So that's another DataStax Enterprise feature. Got to do a little tease for that as well. This is a feature that's inside of DataStax Enterprise that basically speeds up full table scans. And you'll see that you can actually get a lot better performance versus just the open source by using this continuous paging mechanism. All right, just a few more things to talk about, because I talked a little bit before about how we can do this table caching and basically share information between different users, share our data in RAM. So to do that, we use cache statements. So here's the most basic cache there is. Basically, we write cache table, and we name one of our tables that we want to put in memory. This is going to map us down to an in-memory relationship, which is based off of our Cassandra source relation. And to release it, we just call uncache. Now, this is often not what you want, because caching the entire table in memory can be pretty expensive. And more likely, it's going to be like that example that I showed previously, where you want to cache just the data for today, or maybe just the last hour, and then run a series of requests on that. To do that, the syntax is just a little bit different. We just say we would like to cache the table, we name our table, or we name our new cached view, and then we run a select statement which describes what data we want inside of that cache. And then we uncache it the same way we would have uncached a full table. So basically, by using these kind of mechanisms, we can do all of those same things that you were seeing in Scala, that you were seeing in Python, and we can do them without actually writing any of that code. So I hope this has really gotten you interested in all of the things that you can possibly do with this sort of setup. And I've got a whole bunch of links here, which of course will be when the slide deck goes up, you can just click on these rather than having to copy them down, on a whole bunch of the things I talked about today. And I would be glad to take any questions you have on this setup or using Cassandra and Spark. So thanks so much for coming out.
I think we're going to do 5 minutes of Q&A. There's one mic over there, and anyone near me can grab this.
Hey, I'm wondering how the pushdown will work for the join queries. Say if I have a table and join with another table based on partition key, does it able to just load a subset, or have to scan both of the tables at the same time?
Currently, it has to scan both of them. This is something that we're actually working on pretty hard. It's been a while. We've been waiting for Catalyst to get to a point where we can actually implement that as a strategy. But obviously, since you don't actually expressly say that, it's not something that happens automatically at the moment.
Okay.
There is an option we have in our RDD API, which is not accessible through Spark SQL that you can do it with.
Yeah, that's what we're currently using. So if you guys can make that happen, then we can switch everything to the Spark SQL.
Yeah, I mean, believe me, I know it'll be great to have it in there.
Cool, thanks.
A question.
No.
When you showed the where statement, we had C, say, greater than 2, and that was a single clustering key. What happens if the table had, say, 2 clustering keys, say, for instance, C1 and C2? Can we still do the where C1 is greater than 2, but then leave C2 out of the statement?
Yes, you can. Basically, any query that would have been valid in CQL, we are able to understand and reshape it. So basically, if you have multiple clustering keys, the only requirement is that you have them in order that they appear in the statement. You don't actually have to write them, but if there is a first clustering key, you need to have the first clustering key for the second clustering key to make sense.
Yep.
Right? But as long as you have all of those in order inside of your statement, then you're good.
Okay, well, so what happens if I didn't? So say I did C1 is greater than 5, but I never defined what I wanted C2 to look like.
So if C2 is after that in the clustering key order, you're good.
Okay.
If C2 is first in the order, like the clustering key is C2, C1, then it's no good because there's no basically way for Cassandra to do that optimization. You have to full scan anyway.
Okay.
So you showed the FIFO mode in the Thrift Server accepting requests, and then you showed the rather fair scheduler. I didn't get that part. Do you have to do something to enable the fairer scheduling, or was...
Yeah, to turn on the fair scheduler, so this is inside of the Spark documentation. I didn't put it up there, but basically you set Spark, I'm not even going to try to remember it off the top of my head, but there's a something.fair scheduler, and then you basically, I forgot to say this, but there's actually a lot of other options. You can set up different pools where different users have different priorities, and you can do all sorts of different balancing based on your particular needs.
So it's one of the configuration options for the Thrift Server then? Or?
Yep, just --conf. It's actually something you can use for all Spark applications, but it mostly makes sense when you have multiple clients using a single Spark context.
Thank you.
I had a question on the cast which you use in the Spark SQL. So is it a Spark or is it just a SQL function, which is cast is mostly SQL, right?
The cast that I did?
Yeah.
So now, like I said, there is really no differentiation anymore, right? It's going through a Spark parser, which is picking that up. So the cast is a data frame cast, so it's not a Hive function. There are still a few, I think, legacy Hive functions littered throughout the code base, but as UDFs and things like that, but most of them are being changed over to be native Spark.
Which version? So which version does it?
What version?
Of Spark or
5.2 or it will support 4.8 something?
What?
DataStax.
Oh, DataStax? The latest version supported by DataStax is Spark 2.0.2.
How would you deal with like wide column data?
What was that?
Like how would you define your SQL statement if you had that wide column data for Cassandra? Like you didn't know your column names in advance.
So this is really only for SQL 3-based applications. There's really, you can do this with the old Thrift API, which I assume what you're discussing, where we basically have a long list of cells and values, and because of that, we basically have an unlimited amount of columns. With that approach, I think this will use, I think the way that the Java driver reads it, which is how we actually get this information, comes out as a entity value sort of thing. So you'll basically end up with key value, well, it'll be partition key, entity name, and then value. So you'll get triplets. Okay. So I'm pretty sure that's what it gets ended up read as, but it's been a while since I've checked that. One thing to remember is that Thrift is deprecated in Cassandra and is going to be fully removed in 4.0. Someone want to thumbs up on me? 4.0, so beware.
All right, I think we can continue the questions outside. Round of applause for Russell. Great talk.